Hello everyone. In this video we have to see about the atomic phase structure calculation of FCC cubic structure. In this video we have to calculate, in addition to that, coordination number, atomic radius, how to calculate the atomic radius of FCC structure, and some of real world applications of the calculation of the APF, that is atomic packing factor. The first, why need to calculate APF, that is atomic packing factor? According to the packing of the atoms, the physical properties are changing. So crystal packing density increases as that some of physical properties, physical chemical properties and mechanical properties will changes. For example, you can see the graph. So crystal packing density increases, so ionic conductivity exponentially decreases. Whereas electronic conductivity increases while increasing the crystal pack density. So this is the pictorial representation of atomic lattices. So green and blue, or the green and yellow are the lattice, atomic lattice points. So you can see that easily identified. So this is a closed packing structure, that is closed packing structure and densely packed structure. Based on that, the movement of electrons and the atoms mobility of electrons in these lattices and conductivity will be varies. So based on that, physical property is the main factor for that atomic packing factors, and physical property designing is called as, generally known as structure property relations of atomic crystalline materials. So now we have to some of characteristics of the unit cell. We have to see about some of characteristics. First of all, we have to see about the number of atoms per unit cell. It's about 12. So FCC has number of atoms will be the 2, and coordination number will be the 12. So coordination number is nothing but the nearest number of atoms of a particular unit cell. Number of nearest atom of a particular atom in the particular unit cell. For FCC, it has about 12. Next, the distance between the nearest atoms, the atomic radius will be calculated, and finally we have atomic packing factor density. From that formula, it is nothing but the ratio of the volume occupied atom to the volume of the total unit cell. So that is called as a APF, atomic packing factor. So this is the pictorial representation of a face and the cubic cell. You can see that the simple cubic and corners have 8 atoms, and in addition to that we have a faces, 6 faces have a central atoms, that is called a face centered cubic cell. So this is A, B, C are equal, and 3 different faces have a in a center of atoms. So this is the calculation. You can see that the pictorial representation of a coordination number, that is highlighted in the simple cubic structure, have a different faces, and you can see the radius diagram. So here have a atomic cutout image of that atoms present in the FCC structure. So you can see that you can cutting the closed packing structure of FCC, the crystal atoms will be cut into like the picture which is shown here. So these are the cutout images of the FCC and schematic diagram of FCC structure. So finally we have to calculate number of atoms in unit cells are 4 called. So corner atom share the atoms by 1 is the ratio as simple cubic structure, and 6 faces atoms having the shares of the 6 unit cell. So 6 to the half of the unit cell will be 3. So 3 plus 1 will be 4. So number of atoms present in the unit cell is 4. And atomic radius, from that we have to calculate Pythagoras theorem of A, B, C. Using that Pythagoras theorem of this triangle, we are taking the triangle by drawing, taking account to the center of the face of the atom. We can calculate and derive atomic radius of FCC number root 2a by 4. So finally we have to calculate APF, that is the volume of all atom, and to the volume of total volume of the unit cell will give the APF, atomic packing density of that FCC structure, about 74% or 0.74% is called as how much the atoms densely packed in the FCC structure. The remaining part will be the atomic packing, remaining part of 74, after that 74% is called as a empty space. So applications of crystals, especially closed pack structures, will be used for finding calculation of every different field in this real world application. Some of memories and random memories and physical memories, fabrication of microprocessors, RAM and positions, sensors and accusers, fuel cells, catalyst, solid state, temperature state, solar cell, some of electronics will be fabricated according to the structure property relationships. So in particular direction and directionality in crystals having different properties, And directionality, anisotropic, that is called as anisotropic nature. Anisotropic nature only depends on that atoms present in that particular direction. That is indirectly mean that the density of atom in a particular direction is the reason for the physical property of the crystal on particular direction. So that is the main reason of anisotropic nature of a crystal in a particular direction. That will be only the structure property relations will be valid. So in this class we have stopped here. Next class we have introduced some of the practical application of that BCC and practical application of the crystals in a real world. So here I show some of references, so you can go through for the study. And finally, thank you for it.